Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Afiq Mamin bin Ahmad Rizwan from 2 PPISMP Mathematics 1. Okay, so today I would like to present my assignment of the course MTES 1142 Computational Thinking in Mathematics. Okay, the title of my project is the Circuit Engineer, the 5-meter Grand Prix Challenge. Okay, now you might wonder why circuit engineer. Okay, it's because in our primary school mathematics syllabus, students often find the topic of length and unit conversion, specifically between millimeters, centimeters, and also meters, to be quite abstract and dry. Okay, by framing this as an engineering challenge, we transform a standard classroom lesson into an immersive and hands-on mission. Okay, so the core objective of this presentation is to demonstrate how we can integrate computational thinking, which is CT, skills to solve non-routine mathematical problems. Instead of just asking students to convert units on a worksheet, we are challenging them to think like engineers. They will need to navigate through complexity, identify patterns, and also design a logical workflow to build a race track that is exactly 5 meters long. Okay, throughout this 20 minutes presentation, I will be breaking down the fundamental concepts of the computational thinking and heuristics, and also I will also walk you through a detailed 60-minute lesson plan designed for students, showcasing how activities like the gallery walk can foster collaborative problem solving. So by the end of this video, we will see how CT serves as a powerful framework that empowers students to tackle challenges with confidence and precision. So let's begin our journey into the world of computational thinking. Moving on to the second slide, to ground our project in the national curriculum, this presentation focuses on the year for mathematics syllabus, specifically under the theme of measurement and geometry. Okay, the main topic we are tackling is length, which is chapter 5 in the KSSR 27 textbook. As we can see on the slide, this chapter covers several essential units of measurement that students must master, which is millimeters, centimeters, and also meters, and also kilometers. Okay, in this project, we are placing a heavy emphasis on learning standard 5.1, which involves the relationship between different units of length. Specifically, we are looking at the conversion between millimeters and centimeters, as well as meters and kilometers. For many students, these conversions often feel like just a series of multiplication or division by 10, 100, or 1000. However, the goal of the circuit engineer challenge is to move beyond the root calculation. I chose this specific topic because unit conversion is a foundational skill that appears in various real-world scenarios, from construction to tailoring. However, it's also a topic where students frequently make logic error or struggle to visualize the actual physical distance they are calculating. On the right side of the slide, you can see the 4 main pillars that we will be applying in our circuit engineer project. The first, decomposition. This is the act of breaking a large problem into smaller, more manageable parts. Second, the pattern recognition. Here, students look for similarities or trends that can help them to solve the problem more efficiently. And last, abstraction. This is where we filter out irrelevant information and focus only on what matters. And last, algorithmic thinking. Finally, we develop a step-by-step set of instructions to reach the solutions. By introducing CT skills, we are giving the students a mental framework to verify their own logic. By the end of this lesson, students shouldn't just know how to convert 1.2 meter to 120 cm. They should understand how that measurement fits into a larger system, like a racetrack circuit. In the next slide, we will look deeper into what CT actually means and why it is perfect tool for this mathematical journey. Let's explore the definition of CT together. Now we arrive at the heart of this presentation. What exactly is computational thinking means? Often when people hear the word computational, they immediately think of coding or computer programming. However, as I have highlighted on this slide, CT is primarily a problem-solving process. It is a mental framework that allows us to take a complex, messy problem and express it in a way that a computer, or even more importantly, a human, can execute effectively. It is crucial to understand that CT is not about thinking like a computer, which is literal and rigid. Instead, it is about thinking with the logical power that computers use to solve problems. In the context of our Year for Mathematics classroom, CT acts as a bridge that connects abstract concepts to logical solutions. It empowers students to move away from just guessing and towards systematic reasoning. In this presentation, I will show how these city pillars work hand in hand with mathematical heuristics. While heuristics provide the specific strategies like drawing a diagram, computational thinking provides the logical structure to ensure those strategies are applied correctly. It is about building a toolbox of mental skills that students can use for any non-routine challenge they face. Now that we understand the framework of computational thinking, we must look at the specific tools we use to execute that logic. These tools are called heuristics, as shown on the slide. A heuristic is essentially a rule of thumb or a mental shortcut. In a mathematics classrooms, heuristics are strategies that students use to solve problems when there is no obvious or immediate formula to follow. Unlike routine math, where you might just multiply two numbers to get an answer, heuristics are designed for non-routine problems. They help students get started when they feel stuck. Instead of starting at a blank page, heuristics encourage students to take action. As I have listed here, common mathematical heuristics include drawing a diagram, making a systematic list, working backwards, or even trial and error. In our circuit engineer challenge, heuristics play a vital role. For example, when Aiman needs to connect track pieces of different units, a student might use the heuristic of drawing a diagram to visualize how 800mm looks next to 1.2 meter. Or they might use trial and error to test different combinations of track pieces until they hit the 5-meter mark. Heuristic turn abstract numbers into practical visual solutions. To summarize, if computational thinking is the architecture of our thoughts, then heuristics are the hammers and nails we use to build the solution. When a student combines these two, they stop being calculators and start being problem solvers. This synergy is exactly what we need for the 5-meter Grand Prix challenge, which I will explain in the details in the next slides. Now, let's look at the actual challenge I have designed for the Year 4 students. Meet Aiman. Aiman wants to build a toy car racetrack in his living room, but he doesn't want it to be just any random track. He wants a professional circuit that is exactly 5 meters long. So to do this, he has 3 types of track pieces in his toy box, but there is a cache that are all measured in different units. As you can see on the slide, there are materials Aiman has here. Track A, which is 250 centimeters long, track B, which is 1.2 meters long, track C, which is 800mm long. The question we are posing to students is how many of each track piece should Aiman use to make the total length exactly 5 meters? You might ask, why is this considered a non-routine problem? In a routine problem, a student might simply be asked to convert 5 meters to centimeters. That is a direct one-step calculation. However, this problem is non-routine because first, there is no single formula. Students cannot just plug these numbers into a calculator to get an immediate answer. Second, it is an open-ended challenge. There isn't just one correct combination. Students can use different quantities of A, B, and C to reach the goal. Next, it requires multi-step reasoning. It forces students to bridge the gap between different units of measurement before they can even begin the addition process. By presenting the problem this way, we are moving away from boring worksheets and moving towards a real-world engineering scenario. It creates a need for the students to use math to solve a physical problem. This sets the stage perfectly for the application of CT skills, which I will demonstrate in the following slides. Now, we will look at how we apply the first pillar of CT skills, which is decomposition. As I mentioned earlier, decomposition is the process of breaking a complex problem into smaller, more manageable parts. Okay, for a year for students, looking at a 5-meter target with 3 different units, millimeter, centimeter, and meter, can be overwhelming. Decomposition helps them to stop feeling stuck and start taking an action. As shown on the slide, we guide the students to decompose IMOS challenge into 4 key sub-problems. First, identify the goal. The final length must be exactly 5 meters. Second, identify the constraints, which is we have 3 types of track pieces, each with a different units of measurement. Third, deal with the units. We can add 250 cm to 800 mm directly. So a smaller task is created, convert all this measurement into a single base unit. Fourth, finding the combination. Instead of guessing the whole track at once, students calculate how many of track A they might need first before moving to track B and track C. By breaking the problem down this way, the Skerinan routine problem becomes a series of simple mathematical tasks. Students are no longer trying to solve a 5-meter puzzle. They are simply converting units and doing basic addition. This is the power of decomposition. It reduces the cognitive load and allows the student to focus on one small victory at a time. If you look at the diagram on the slide, you can see how the big mission at the top is connected to the smaller action steps at the bottom. This visual representation is exactly how we want our students' minds to work. Once they have decomposed the problem, they are ready for the next step, which is looking for the patterns to make their work even faster. Now that the problem has been broken down into smaller pieces, let's see how pattern recognition helps Ayman's team identify the relationship between these different units of the length. The second pillar of the composition thinking that we apply in this project is abstraction. In simple terms, abstraction means filtering out irrelevant details and focusing only on the information that is necessary to solve the problem. For students, a problem like building a racetrack can come with many distractions that could their mathematical judgment. As you can see on the slide, we teach the students to perform abstraction by separating the story from the map. What is irrelevant? Details like the color of the track pieces, the brand of the toy cars, or the fact that the track is being built in the living room. These are fun details for the narrative, but they don't help in the calculation. What is essential? Only the numerical values and their respective units. 250 cm, 1.2 meter, and also 800 mm. By focusing strictly on these numbers, students reduce the complexity of the task and avoid information overload. In the context of our circuit engineer project, abstraction allows students to simplify the problem into a clear mathematical equation, which is x plus y plus z equal to 1500 cm. This mental leap is vital. It teaches students that in engineering and mathematics, clarity comes from knowing what to ignore. Once they have stripped the problem down to its core data, they can move forward without being distracted by the aesthetics of the circuit. With the relevant data clearly identified through abstraction, students are now ready to design a systematic plan. So let's move to the final city pillar, which is algorithmic thinking, to see how they create a step-by-step manual to complete the track. Now we reach the final and perhaps the most practical pillar of computational thinking, algorithmic thinking. Okay, simply put, an algorithm is a set of step-by-step instructions to solve a problem. In our circuit engineer, once the students have identified the key data, they need a master plan to ensure the track pieces are combined correctly to reach exactly 5 meters without any errors. As you can see on the slide, we have developed a clear algorithm for Ayman's team to follow. Step 1. Standardize the units. The first instruction is to convert all measurement into a single base unit, which is the centimeters. We convert 1.2 meter to 120 centimeter and 800 millimeter to 80 centimeter. So second step, the completion strategy. This is where students use the heuristics of trial and error or making a table. They test different quantities. For example, what if we use one piece of thread A, two of thread B, and one of thread C? Step 3, the verification step. The final instruction is to sum them up. If the total equals exactly 500 meters, the mission is successful. If not, they must debug or repeat step 2 with a different combination. What makes this algorithmic approach so powerful for your for students is that it creates a repeatable formula. Once they understand this sequence, which is standardized, combine, and verify, they can apply the same logic to any measurement problem, whether they are measuring mass in kilogram or liquid volume in liters. It moves them away from random guessing and teach them to work with the precision of a computer programmer. With the algorithm in place, our students are ready to move from the planning phase to the action phase. In the next slide, I will show you how this entire city process is integrated into a 60-minute lesson plan, ensuring that every student gets to experience being a circuit engineer. Now let's see how we translate all this computational thinking theory into a practical 60-minute lesson for a year for classroom. As an educator, my goal is to facilitate a student-centered environment where the teacher acts as a lead engineer and the students are the designer teams. I have structured this lesson into 4 distinct phases to ensure smooth flow of ideas. We begin with a high interest, which is set intention. To grab a student's attention, I will show a 1-minute video of high-speed Formula 1 race or display real physical track pieces on their desk. The who here is a question: can we build a professional circuit right here in our classroom? This immediately creates curiosity and sets the stage for the non-routine problems of I-5 meter track. In the first stage of development, students work individually. This is where they apply decomposition and abstraction. I want every student to try and wrap their heads around the units conversions, millimeter to centimeter and meter to centimeter, on their own first. They use their engineer's notebook to jot down the data and begin a rough plan. This ensures that when they move into groups, everyone has a basic understanding of the mathematical logic required. This is the heart of the lesson, the group activity. Using the gallery walk method, students from the engineer teams of 4, they are given a mahjong paper and track cards of different lengths. Here, they must use algorithmic thinking or to build their circuit. They don't just stick cards on paper, they must prove their circuit equal exactly 5 meters. As they rotate to other tables during the gallery walk, they perform evaluation and debugging on their peers' work. So finally, we end with a closure phase. We come back together as a class to reflect. I ask questions like, what was the hardest part? The conversion or the combination? This allows students to realize that computational thinking was the key that made the hard part easier. We summarize the lesson by reinforcing that in math, a good plan and algorithm is set as important as the final answer. This 60-minute journey ensures that students are not just calculating, they are communicating and also collaborating. Next, we will dive deeper into the specific group activity I mentioned, the gallery walk to see the cityscapes in action. Before we look at the results, let's understand the mechanics of this activity. How does the racing table actually work in the year 4 classroom? First, we have the formation phase. The students are divided into groups of 4, which we call the engineering teams. The small group size is intentional, which is ensure that every student has a specific role and no one is left out of a computational thinking process. Next is the task. Each team is provided with a large mahjong paper and a set of track cards. These cards represent the 3 types of track we discussed earlier: track A, track B, and also track C. Their mission is to design and build a circuit by sticking these cards onto the paper. However, there is a strict engineering requirement. The total length of the connected cards must equal exactly 5 meters. This forces them to apply the algorithm we designed, convert, combine, and also verify. The final phase is the rotation, which is the gallery walk element. Okay, once the tracks are built, one member stays at their station as the lead engineer to explain their group's logic. The other 3 members rotate to different tables or stables to inspect the work of other teams. They carry a checklist to verify the calculations of their peers. This rotation is crucial because it exposes students to different ways of solving the same non-routine problem, broadening their understanding of pattern recognition. Now, let's dive deeper into the heart of the classroom activity, which I have named the racing stable. This is a gallery walk activity designed to promote activity communication and collaboration. In this phase, the classroom transforms into a series of engineering workshops where each group is tasked with constructing their own 5-meter circuit. But more importantly, this is where we see the social application of computational thinking. First, we look at the collaborative decomposition. Within their groups, students don't just guess the layout, they discuss and break the 5-meter goal into segments together. One student might manage the millimeter pieces while another handles the meter pieces. Then, as they move from one table to another during the gallery walk, they engage in peer-to-peer pattern recognition. They start to see patterns in how other groups solve the same problem. For example, they might realize that Group A used more 800 meter and 800 millimeter pieces to fill small gaps, whereas our group relied on the 250 cm pieces to cover distance quickly. Next is shared algorithmic thinking. Before any piece of is glued to their margin paper, the team must agree on a master plan or an algorithm. They follow the logic, convert, combine, and verify. A key part of this stage is debugging. If a visiting group finds that a team strike is actually 505 cm instead of 500 cm, they provide feedback. The original team then has to debug their algorithm, identify where the conversation or addition went wrong, and fix it. Feedback loop is a vital CT skill that mirrors real-world software engineering and design. Finally, the group evaluation serves as the feedback loop. By using a checklist to verify the requirement, which is the 5-meter total, students are practicing evaluation. They learn that in mathematics, the process of verifying a solution is just as important as finding it. This activity ensures that CT is not just an environmental exercise, but a collaborative journey of discovery. Through the racing stable activity, the abstract numbers from the textbooks become physical, measurable, and debatable. Now that we have seen the action in the classroom, let's move to the final part of my presentation, which is the conclusion. To conclude, our circuit engineer project successfully demonstrates that CT skills is a game changer for year 4 mathematics. By turning a dry topic like unit conversion into a hands-on mission, we help students see the logic behind the numbers. We have seen how decomposition, abstraction, and algorithmic thinking allow students to tackle non-routine problems with confidence. They don't just solve a math questions, they learn to debug errors and think like engineers. This shift from rote learning to active problem solving is exactly what the KSSR curriculum aims for. Ultimately, integrating CT into our lessons prepares our students for real-world challenges. It builds their analytical skills and resilience. That is all from me. Thank you for your time and for joining me in this 5-meter Grand Prix challenge. Thank you.